basically this is what we were doing right before we ended last time. We were talking about the absorption spectrum of chromium, or I guess it would be hexaqua chromium 3. And we were talking about, the fact that we could predict only one transition here if we were just looking at the lower energy set and the higher energy set. But in fact, the blue spectrum is more of what you see. And there are actually 4 different electronic transitions. And so we talked about the fact that in multi-electron molecules or multi-electron metal ions, you also have to consider the fact that electrons repel each other differently when they're in different orbitals. So promoting something from a dxy to z squared is different than promoting something from the xz to z squared. And a simple explanation of that is when you have an electron that's already in the z axis and you promote it to z orbital, there's less of a change than when you go from the xy plane, that's pure xy, to the z orbital. So now we have to consider something, and we're calling these things microstates. So basically the different possible electron configurations are called microstates. The idea is that if you have 5 d orbitals in an octahedral field, so this is d1, this metal ion was d1, this electron configuration is not the same as this electron configuration. So these are not equal. And this would also be different from this one. So there's multiple ways that you could write these electronic states. But it's also important to realize that this is different from the first. So depending on whether your electron is spin up or spin down would give you a different electronic configuration. And these different states are represented by something called Russell-Saunders terms. I could assign this first one as a D2, or this is called a doublet D. I could assign the second one as a doublet P, and the third one as a doublet S. And then this one here would be a singlet D. These are Russell-Saunders terms. I'm going to define those in a second. But for every single microstate, there's a Russell-Saunders term. And it's something that you can do a systematic analysis of all of the microstates and find all of these Russell-Saunders terms, but we're not going to do that in this class. There is an explanation in your book how to do that. But the important part is to be able to find the ground state term. And so that's what I'm going to teach you now. And the whole purpose of our class today really is to understand electronic spectra of multi-electron metal ions and to be able to find the delta O. Remember that delta O is what we're interested in. Fortunately, we don't have to find all of the microstates, but we can just find the ground state. The reason that we don't have to go through and find all of the microstates is because we can use a cheater way and just use a Tanabe-Sugano diagram. This is kind of like when we were doing point groups. We didn't have to find all the operations. We could just use the character table to help us. In this case, we're going to be interested in electronic transitions, not between orbitals anymore, but between microstates. So we have to know what the microstates are, and all we have to do is find the ground state and know the d electron count, and we can use the Tanabe-Sugano diagrams to help us find everything we need. So we can take a shortcut and use these Tanabe-Sugano diagrams. So these diagrams can be found for any different type of coordination geometry. We will only be focusing on the octahedral field, and you can find these in the appendix of your book, the resource section. So one thing you do need to know how to find is the ground state term. And when you're going to do this, you can actually just consider the free metal ion. You don't have to consider the ligand field. And that means that when you look at the d orbital configuration, you're thinking of 5 degenerate orbitals. So when you found the ground state term, you just think of the free metal ion, no splitting of the d orbitals. So this is how you do it. The first thing is to determine the number of unpaired electrons. In the case of metal ions, that means we have to know the d electron count. So this is another use for just being able to look at the periodic table and understand what the d electron count of a metal ion is. And let's use the D1 case. This is a very simple case, but let's use this as our example. So in this case, you only have one unpaired electron. The second thing you need to do is calculate the spin multiplicity. For this, you need to know S. So we're going to call this 2S plus 1. And S is a new quantum number. It's a capital F, and it's related to little m sub s. So it's the sum. It's basically the sum of all of your m sub s numbers. So in this case, we only have one unpaired electron. It would have spin 1/2. So remember that little m sub s is equal to plus 1/2 or minus 1/2. So in this case, this is equal to 2 times 1/2 plus 1. The other way to do this, and the kind of the cheater way, is just, this can just be the number of unpaired electrons plus 1. So either way you think of it, this will get you to the right number. So in this case, the number is 2. Then the third thing to do, after you have the spin multiplicity, in this case it's 2, and that means it's a doublet. You calculate the maximum possible value of another new quantum number, m sub l, but it's capital M sub l. And m sub l is simply the summation of all the little m sub l values. And remember what those m sub l values are. If I take my d orbitals up here as an example, normally you start writing at -2, -1, 0, +1, and +2. At least that's how I do it. So as I've written this electron configuration, I have not maximized my value of m sub l. So I need to put this electron into the maximum possible value, so that in this case my m sub l value is maximized and it's a 2. The m sub l values, just like L, like little m sub l, if a little m sub l equals 0, you have an s orbital. If little m sub l is 1, you have a p orbital. In this case, you have the same correlation. If the the capital M sub l is equal to 0, 1, 2, or 3, you're assigning a letter value, S, P, D, and F. But these, again, are capital letters. Capital M sub l relates to another quantum number, L. So this is a new quantum number. And it's simply it's like the sum of the m sub l vectors. So these are analogous to your s, p, and d orbitals, but it's not a literal translation. It's not literally the same thing, but it's similar. And then the last thing to do here is to simply write the term. So after you've gone through step 3, you have all of the materials you need to write the term symbol. So you write the term symbol, and this is called the Russell-Saunders term. And the term symbol is simply the letter for the m sub l value, and your spin multiplicity that you calculated in step 2 is a superscript on that. So for our D1 metal ion, our m sub l value was 2, and so we would write a D, and our spin multiplicity was 2. So it has a superscript of 2 on the left-hand side. And this is read as a doublet D. So a 1 for spin multiplicity is a singlet, a 2 is a doublet, a 3 is a triplet, a 4 is a quartet. Okay, so this ground state term describes the ground state microstate of the free metal ion. And this is useful to us, but what we really want to know is the electronic transitions that will happen in the metal complex. And so we're going to have to ask the question, what will happen to this doublet D in a D1 metal ion when it's exposed to an octahedral ligand field? And the answer is that just like the degenerate d orbitals split into higher and lower energy sets in the octahedral ligand field, the ground state term will split. And it actually splits just like the d orbitals do. So I'm going to write something called a correlation diagram here. And this is the energy on the y-axis. And I'm going to put my D ground state here. So this is my doublet D. Remember, this is for a D1 metal ion. So this is a simple case. So here's free. I'm going to write over here the octahedral ligand field. And it turns out that the doublet D will split into a lower energy microstate, which is represented as a 2T2G, or a doublet T2G, and a higher energy microstate, which is a doublet EG. And now I'm using capital letters. So really what's happening along this y-axis here is we're having a ligand field. So on one side of the y-axis over here on the left, we have no ligand field. And so we only have 5 degenerate d orbitals. But as the ligand field increases, you're splitting the energies. So I'm going to be splitting the D into 2 different energy levels. The stronger the ligand field, the more they're split. And so this difference here is your delta O. And in a strong octahedral ligand field, you would have an EG orbital set and a T2G orbital set. And the delta O increases as the ligand field increases. What I just drew here is basically 2 extreme cases, the free ion itself and then a strong octahedral ligand field. And then I've just made correlations in between. This is called a correlation diagram. It's also called an Orgel diagram. And it just simply takes the 2 extreme cases and assumes that everything in the middle is a correlation between them. And this one was just for the ground state. It turns out in an octahedral state, or in an octahedral ligand field, you will always split the ground state terms. So I'm going to write the terms for the metal ion, or the metal atom, here, and then I'm going to write what they split to in an octahedral field. And this is really just the octahedral irreducible representation. So you could read these if you knew what the terms meant. So if you knew what S, P, D, F, and G were. So these would be your Russell-Saunders terms for the N sub L value. The S will split into an A1G under the octahedral field, so that's the most symmetric. A P will split into a T1G. The D will split into T2G plus an EG. Do you notice how similar these are to the orbital? So an S orbital would have very symmetric A1G symmetry under octahedral. A P orbital would have a triply degenerate case under an octahedral. So this is a T1G. The D orbitals split into T2G and EG sets. So this is very analogous to what we've talked about before. The F split into T1G, T2G, and A2G. The G microstate is A1G, EG, T1G, and T2G. So with the F and G orbitals, it's a little bit harder to read those directly off of the character table. So these are just for your reference. And if you look at any of the Tanabe-Sugano diagrams that I gave you, you should see that if you start out with an S term on the left-hand side, it will end up in an A1 term on the right-hand side. I would like you just to take those Tanabe-Sugano diagrams and look at them for a second. Just examine them. Find the term for the metal ion and make sure that it correlates to the correct things for the ligand field. Notice anything? They are curved. Yes, some of them are curved. And the curve comes from something called the non-crossing rule. And you'll notice that the ones that are curved are the ones that have more than one microstate that is the same. So basically what happens is if there's 2 microstates or the 2 terms that are the same, if they're trying to cross each other, they actually bend away from each other so that they don't cross. Do you notice anything else? Do you notice that there aren't any G subscripts? Right? That's because in an octahedral field, all of the subscripts are G for those guys, and so they just left them off for simplicity. So all of the terms on the right-hand side should have G subscripts, but they just left them off for simplicity. I think it's confusing. I don't know why they did that, but my biggest concern is that you can understand the logic of using these things. So if you can, if you tell me T1 instead of T1G, that's fine. But in your reading, don't let it confuse you that the actual diagrams do not have the subscripts, but when they describe them in the text, they do have subscripts. And at least for me, it's a little confusing if you don't know that. Now, the correlation diagram I just drew up here is a much simpler version of those Tanabe-Sugano diagrams. So let's talk about what's different about the Tanabe-Sugano. These are correlation diagrams. So on the left-hand side, you have the ground state terms, the terms for the metal ion itself. On the right-hand side, you have a strong octahedral field. So these are correlation diagrams, but they're special in the fact that they take electron-electron repulsions into account. So these Tanabe-Sugano diagrams are interesting. They show the relative energy differences of the terms. So you can basically use these to quantitate your data. So if you know what your y-axis value is, you can read across and you can find the x-axis value. That's what you're going to use these for. So these show relative energies of different terms, and all of the things that you'll see on those diagrams are determined experimentally. So you would never be able to generate one of these diagrams unless you were doing some serious experiments with spectroscopy. The x-axis here is not zero, so it's not zero energy. These are plotted with the ground state term itself. So whatever the lowest energy is. So this correlation diagram that I drew, if you redrew this diagram so that this ground state line was the x-axis, you would get a Tanabe-Sugano diagram. So these are plotted with the ground state term on the x-axis. And what that means is that the diagrams directly correlate to the energies of the states with respect to the ligand field. So you can literally read from the x-axis up, and you would get the energy of that transition. So let me say that a little bit of a different way. If you look at the x and y axes, you'll see that these are plotted in terms of delta O over B. And B is the Rocca parameter. So it's delta O over B on one axis, and E, or the energy, over B on the, I believe the delta is on the X and E is on the Y, where your B is called the Rocca parameter. And we mentioned this earlier. This Rocca parameter accounts for electron-electron repulsions. So this B, so the Rocca parameter summarizes the electron-electron repulsions between the electrons in the d orbitals. I will only ask you to calculate a delta if I give you a B or a Rocca parameter. So you need the Rocca parameter to be able to interpret your Jahn-Teller diagrams. Or if you're given other data like the energy or the delta O, you can derive the B or the Rocca parameter from that. And I'll show you an example in a minute. So what these Tanabe-Sugano diagrams are used for is you are going to use them to determine the delta O from absorbance spectra, or you can use them to predict the identities of transition. So in this spectrum I drew up here, back here, I can look at my Tanabe-Sugano diagram and I can predict what transitions are leading to these absorbances. So there's two purposes that we'll use them for. Calculating delta. So we'll use them for calculating delta of multi-electron complexes. We'll also use them for interpreting the spectra. or identifying transitions. Before I show you how to use the Tanabe-Sugano diagrams to interpret a spectra, I want to talk about selection rules for electronic transitions. So there are some rules. So transitions happen, but they can't all happen with the same intensity because of these selection rules. So the first one is called the spin selection rule. And the spin selection rule is that the delta S cannot be 0. So this means is that spin multiplicity cannot change. So transitions between states of different multiplicity are forbidden. So if you have a 4A ground state, you could do a transition to a 4T. This is okay. Because the 4 is your multiplicity, it does not change in that transition. But if you start from a 4A, you cannot go to a 2T. So this would be a forbidden transition because the spin multiplicity changes. So if you look at your Tanabe-Sugano diagrams, let's just pick the first one, the D2 case. So from the ground state, how many allowed transitions do you have? And what I want you to pay attention to when I ask you, so let's say in an octahedral field. So look at the the right-hand axis. What's your ground state term for D2 in an octahedral field? Yeah, triplet T1. Triplet T1 is your ground state term. So how many other triplet terms are there? 1, 2, 3. Yeah. The A, yeah. So that's showing you that it's a high energy. What it means, though, so what is the most likely transition that you'll see? 3. So it would be a triplet T1 to the triplet T2 would be the most likely. That's your lowest energy transition. The triplet T1 to another triplet T1 is also probably likely, right? But it would be a higher energy transition, whereas the A3 or the triplet A2 transition might be a little bit too high of an energy. But you'd have to look at the spectra and determine if there was 1, 2, or 3 transitions, you can make those assignments based on their relative energy. Okay. So the second spin selection rule, the second selection rule is called the Laporte selection rule. And this one says that there must be a change in the parity for centrosymmetric molecules. There must be a change in parity in centrosymmetric molecules. What's a centrosymmetric molecule? Look at that word, centrosymmetric. Center of symmetry, maybe? Centrosymmetric molecules are ones that have centers of symmetry, or in other words, an inversion center. And the parity is its symmetry with respect to that inversion center. So things like G to U or U to G, so you can have transitions where you're going to and from G to U or U to G. These are allowed, but G to G, U to U are not allowed, or they're forbidden. So those are the 2 selection rules that you need to know. Forbidden does not mean it doesn't ever happen. So this is kind of like the Pirates Code again. It's more like guidelines than actual rules. Forbidden means that it happens less often. And it's not that the forbidden things happen because you can break the rules. The forbidden things happen because molecular vibrations or molecular motions change the symmetry of the molecule temporarily. So anytime you have a vibration, you can have a temporary change in the symmetry, which allows one of those forbidden transitions to happen. It's not breaking the rules, but it's changing the molecule. So forbidden just means that it happens less often. And the forbidden absorbances, or the absorptions, will happen, but they're usually weaker. So the forbidden transitions are usually weak. Your textbook says they're somewhere between 5 to 50 as far as their extinction coefficient goes. Whereas an allowed transition would be more like somewhere between around 100, I think, usually. The ones that I deal with in my chemistry lab are actually 100 for the allowed transitions. A consequence of this is that octahedral complexes are always very weakly colored, or they don't have very intense absorptions. And this is because all of their transitions, their D to D transitions, are not allowed. And an example of this, and I don't have an example to show you, I apologize, but manganese 2+ with 6 waters. This is a nice centrosymmetric molecule. It is a really light pink. It's almost colorless. And it's an example. So, I mean, if you probably have seen a solution of copper 2+, it's like a light blue color. That's another one. It's really light colored. Whereas something that has a different symmetry can be much darker. So tetrahedral complexes are usually a little bit more intense. So that's usually any of the first row transition metals with 4 ligands, unless it's a square planar nickel. But those are usually, when they have 4 ligands, they're a little bit more intensely colored. So you can go into the stocker and dig around if you want to. But the reason, again, is because octahedral, we have a T2G and an EG. So these transitions here are forbidden because of the Laporte selection rule. They happen, but not very often. Whereas in a tetrahedral case, you're dealing with an E and a T2 set. Remember, those do not have G subscripts because there's no inversion, and these are allowed transitions. Okay, so now I want to go back to the hexaquachromium case, and I want to assign the transitions and look at what the delta O is. So I'm going to regenerate the spectrum here. We had a really weak transition, and then 2 medium transitions, and then a really huge shoulder. So we said that was 4 different transitions. So this is chromium 3+, so that's a D3 metal ion. If we want to find the ground state term, we just consider the ion without any ligand field around it, so let's find that ground state term. So I'm going to give you a few minutes. I want you to go back in your notes and look at what the process was, and I want you to try to do this. What's the first thing you do? Okay, how many we have? Yep, so the spin multiplicity is 4. And the M sub L value is, so this is where you want to put them, so in the highest numbers, right? So I'll just start from +2, +1, or 0. -1, -2. So now I have my electrons in the highest possible values that they can go. So what's my value of capital N sub L? What's the number value? 3, right?
Yes.
So this is 2 + 1 + 0, which is equal to 3. And that does correspond to F, right? So 0, 1, 2, 3, that's S, P, D, and F. So this is what we have. And then the last thing to do is just to write the term. And so the term is quartet F. We know how many d electrons we have, and we know our ground state term. Now, look at your Tanabe-Sugano diagram. For D3, is a quartet F the ground state term in that diagram? Good. That means you're right. Now, so in an octahedral field, how many spin-allowed transitions would we expect? What are they? We can expect 3 spin-allowed transitions. One is the 4A2G, or 4A2, to the 4T2, or the 4T2G. And then there are two different transitions from 4A2G to the 4T1G. Now, which ones of those are on the spectra that I drew? So this is where kind of you have to do a little guesswork. But in general, remember, our allowed transitions versus our forbidden transitions are a little bit more intense. So if I looked at this spectrum, I would say that this is probably a forbidden transition. These two are spin allowed transitions, and this is something else. So notice that the intensity of the peaks are going to tell me something. So I can assign these two to spin allowed transitions. Which ones do you think they are? What is the lowest energy spin allowed transition? So if this is wavelength, right, this means I have low energy out here and high energy up here. So I'm going to assign this one as my lower energy allowed transition. So the 4T2G, so 4A2G to 4T2G. And by experiment, that's actually the case. What's my next highest energy allowed transition? Yep. Now, you said that there were 3 allowed transitions. Why don't we see 3? But are they of the same energy? No, they're not. So the next one would be even higher in energy. And so it could be either underneath this big peak here, or it could just be so high energy it's off the scale. Okay, so you can make those 2 assignments, and those are actually the case. Again, you can predict, and you can say what you expect, but you would have to do the experiment to confirm. Now, let's talk about this lower energy guy here. So this is a low energy transition, and we're going to say that it's forbidden. What's a forbidden transition that might happen there? It has to be lower energy than the 4A2G to the 4T2G. Yeah, it could be a 4A2G to the 2EG. It could also, there's another one that's right around the same area, right? But that's a really good guess, and that is actually the case. It is the quartet A2G to the doublet EG is the assignment that the textbook makes for this particular thing based on experiment. But you wouldn't really know for sure if it was the double E or the doublet T. But maybe that's why in the actual spectrum there's kind of a couple little peaks there all together, and those are similar energy. So this is the kind of stuff that you can use the Tanabe-Sugano diagrams for. Oh, and before we move on, this guy, when you see a really big peak that's bigger than the other ones, this is a charge transfer. And I'll talk about that in a minute. But anytime you have a peak that's really, really intense, it's probably going to be from a charge transfer transition. The charge transfers are always more intense than the D to D. So if you have a dark complex, like if you have a solution of a metal ion that's really dark or really intensely colored, it may be that it's got a lot of allowed D to D transitions, but it may also be that there's a charge transfer transition, which is different than the ones that we've been talking about so far. So let me ask you a question first related to the energies of these transitions. If I told you that the lambda max of the 4T2G, the transition between the quartet A2G and the quartet T2G, if I told you that that lambda max corresponded to wave numbers of 28,500 centimeters to the negative 1, and I'm going to give you the Rocca parameter. B is equal to 658 centimeters to the negative 1. What is delta? So this is something you can actually read directly off of the Tanabe-Sugano diagram. So look at that Tanabe-Sugano diagram for D3. How would you figure this out? If I gave you the lambda max, or the energy of the transition, and I give you the Rocca parameter, how can you find the delta? So we're looking for delta. Okay, and remember, you have an axis system here where you have E over B on this side, and you have delta over B down here. Okay, I gave you E and B. Now you have to find delta. If you find what this value is, E over B, you'll know where it is on this axis, and you can simply go over and down to get your delta over B, and then solve for delta. So in this case, so we want to find E over B. So E over B is going to be equal to 28,500 centimeters to negative 1 divided by 658 centimeters to negative 1. What number is that? Well, it's about 43. It's 43.3. It's a unitless number. So then you take this and you follow this. You follow this y value to the T2. So if I look at my chart here, Wait, maybe I wrote it wrong. Did I give you a bad example? Oh, darn it. I gave you a bad example. You're right, you couldn't answer this question very well, could you? 43, yeah. Did I write the number wrong? Uh-oh. Okay, so let's do another one. Let's oops. Doctor has screwed up. I'm not sure what I did there, but let's just change the transition. So I said that was the 4. Yeah, let's make it T1. Does that work? Okay, that's probably what I did. So let's do this T1. Thank you. Okay. Okay, so now let's follow that over to 4T1. So we'll find 43 here. Somewhere like that. You're not going to be super accurate about this, and that's fine. So we're going to find that, so the transition we're talking about is the 4A2 to the 4T1. So this transition. Right? So I'm going to take my 440, and if you could use a ruler to be better about this, but I'm going to say it starts right there, and then if I draw this line all the way down, I get something like 36, 37. So that's my delta O over B. And let's say that that's 37. My delta O is going to be equal to 37 times the rocket parameter times 658 centimeters. So what's that number? There you go. That's your delta. Before, when we were given a wavelength or an energy of the transition, we could directly relate that energy to the delta. In the case of multi-electron complexes, we have to use the Tanabe-Sugano diagram. Any questions about those? Well, so what I gave you was essentially the energy of the absorbance, which was the wavelength. I mean, I gave you the wave number, but it was like I gave you a wavelength. And then we calculated the energy of the orbital split here. Okay? So before, we could directly relate the wavelength to that energy, but in multi-electron complexes, you can't make it. You have to use the Tanabe-Sugano diagram because that takes electron-electron repulsions into account. Any questions? Any other questions? Okay. Let's talk a little bit about charge transfer and what that is. These charge transfer spectra are usually intense, so the extinction coefficient I gave you for the D to D transitions, the forbidden ones, were 5 to 50. This is about 50,000. So these are very intense. They usually dominate your spectra. These are sensitive to solvent polarity. And what it is an excitation of electrons from orbitals that are either all on the ligand to on the metal or vice versa. So they're excitations of electrons to or from molecular orbitals that are mostly ligand in character. So when I say mostly ligand in character, that means that they have the energy levels of the ligand in the molecular orbital. So excitation to or from basically ligand orbitals to or from molecular orbitals that are mostly metal in character. So there's two types. You have the LMCT, which is the ligand to metal charge transfer. And this happens with pi donor ligands when those pi donor ligands have high energy orbitals. And the metal has high oxidation state, so its orbitals are low. So in other words, when the ligand and metal orbitals are close in energy, but your ligand orbitals have electrons to donate. So I'm just going to sketch a situation up here where you have the D metal. So these are your metal orbitals, and then you have some ligand orbitals here. You can draw as many as you want. When you form the metal ligand complex, these ligand orbitals don't change very much in energy, and you have a bonding. Actually, it doesn't need to necessarily put bonding, but you have your d orbitals now that have T2G and EG symmetry. Usually, the T2G is your HOMO, your highest occupied molecular orbitals, but you have electrons. So this is your donor set, right? Your pi donor ligands, and the pi donor ligands are of relatively high energy. Your metal is of relatively low energy. So the difference between the EG and the ligand donor set is not very much, and so it's an easily accessible transition. So what this looks like in a cartoon is you have your metal ligand bond. You have ligands with electrons in p orbitals, and you have a metal d orbital that can accept those electrons. So of course, like everything, these orbitals have to be of compatible symmetry. But in this case, the ligand is full. It's got a donor set or lone pair of electrons that can pi bond into the molecular orbital of the metal. And so you got a ligand to metal charge transfer. The other type is MLCT, or metal to ligand charge transfer. And in this case, this happens with pi acceptor ligands. The pi acceptor ligands, or the E star orbitals, need to be low, and the metal orbitals have to be high so that they're close. So in this case, the pi acceptor ligands with the pi star orbitals low in energy, or let's say relatively low in energy. So when do you have pi star orbitals that are low in energy? Did you guys talk about this in organic chemistry with aromatic complexes? They have low energy orbitals. When you have aromatic compounds or conjugated compounds, you will lower the energy of the pi star orbitals and the pi orbitals as well. But in these cases, when you have aromatics, you often have these metal to ligand charge transfers. The metal itself has to have low oxidation state, and that's so that the energy is relatively high. Or in other words, the important part here is that the ligand and metal orbitals are close in energy. But in this case, it's going to be the metal orbitals that are full and the pi star orbitals are accepting. So I'm going to draw a sketch here where I have my d metal orbitals over here. I'm going to put a pi star set that's relatively low for a pi star. my T2G and EG, and I'm doing, of course, octahedral, but it doesn't need to be. And then I have this low energy acceptor. So this is my acceptor on the ligands. And I'm going to say again that my T2G is my HOMO. And so the transition here is from the d orbitals to the ligand. So if I draw a little cartoon of what that looks like, I have my metal ligand bond. On my ligand, I'm going to draw OL. So I have the pi star orbital. So it's an antibonding orbital. And this time, my metal d orbital has the electrons that are going to be transferred. So there's electrons in the metal d orbitals that are moving to the ligand pi star. So these are just like pi accepting ligands. They are pi accepting ligands. So when you have those types of transfers, you have these really intense absorptions, and that's because they're not subjected to the selection rules that the D to D transitions are subjected to. The Miessler and Tarr book for this chapter it's chapter 11 in Miessler and Tarr. It's especially direct. Read chapter 20 in your Shriver and Atkins book, but the section on this is very small, and it doesn't explain things. For example, we just dropped the G subscripts in the Tanabe-Sugano diagram. The Miessler and Tarr is much more focused on the little details. Shriver and Atkins kind of gives you the general overview of the whole picture. So it's a good idea to look at both of those chapters so that you can have the fullest understanding. But if you're struggling with Shriver and Atkins, go to Miessler and Tarr.